Okay, thanks, Pasquale, for the nice introduction, and also thanks for the invitation to give this talk. So yes, I will talk about the cluster expansion method, the basics of the methodology, and some new developments. Okay, so first I will indicate what is this methodology useful for. Then I explain the formalism, how it is done in practice. And then I will talk about this method applied to large parent cells, and also something about a code that we are developing in the Humboldt University. So suppose you have an alloy system composed of two elements or two species. Let's call them A and species B, and then you have a crystal. And then you have a formula, a chemical formula for this a compound that is AX and BY minus X, for instance. So, but as you see here, the formula doesn't determine everything, because the species of type A can be in several different sizes of this crystal. So one question that one can make is which crystal size A and B would occupy. So also one may wonder which sort of crystal structure will form when you put some specific X value here. Also, you may wonder what are the properties of this material for a given X, whether it is a metal or a semiconductor. Also, you may wonder what happens when you study this material at any temperature. So the cluster expansion basically solve all these problems. As for instance here, these are temperature composition phase diagrams of several alloy systems. And these have been calculated with the cluster expansion method in this paper. So for instance, we can look at this plot here. In the x-axis, you can see this is basically a magnesium oxide, calcium oxide alloy. So in the x-axis, you see the atomic percentage of magnesium oxide in the crystal. And in the y-axis, you see the temperature. So from this, you can learn several things. For instance, that the magnesium oxide that dissolves in calcium oxide at low magnesium oxide concentrations. Also, you can see that the magnesium oxide and calcium oxide separate into different phases at intermediate concentrations, and also that calcium oxide will dissolve in the magnesium oxide matrix at higher concentrations. Also, for instance, in a silicon-germanium system, you will find out that there is a miscibility gap in the silicon-germanium alloy, meaning that in the whole composition range at low temperatures, the crystal separates in two different phases. One is pure silicon and pure germanium. So all this sort of information you can access through the cluster expansion method. So then basically we are answering the question of what's the energy of formation of arbitrary atomic arrangements. This is the information you need to build any of those phase diagrams. Also, with this knowledge, then you can find answer to this important question, that what are the most stable atomic arrangements at different temperatures. And also, you can also access the material's properties at arbitrary alloy configurations. So, how is this done? I will show now a bit how this method can be worked out, let's say, by hand. So with a very simple example. So suppose you have a crystal. Here, the blue circles represent an atomic species of type A. And the red circles that will appear here in the next slides represent atoms of certain species type B. So in this crystal, as you see, is very well ordered. You have a parent lattice. So this parent lattice is repeated in every small square that you see here. But you can build a supercell and make different configurations of the atoms of type B in the supercell. In this case, I am just indicating a supercell composed by 16 different sites. so it's a 4x4 supercell. And the number of possible arrangements here, without taking into consideration symmetries now, just as an example, is 2 to the m. So for n equals 16 lattice size, you have this number of configurations. So as you can imagine, doing this number of ab initio simulations for every one of those configurations is something that is out of reach. Therefore, what we can do is to build a model, and this is done in the following way. So you start with the pristine lattice that is filled only with atoms of type A, and then you make an ab initio calculation. Yes? And then you get an energy, and you call this energy J0. So this is a parameter that in the next steps we keep it fixed. Then you put just an atom of type B in some crystal site there. Then you make the ab initio calculation for this crystal, and you get the energy. So this parameter we had from the calculation that we did before. Therefore, the difference between this and this represents an additional energy contribution that we call J1. So this parameter J1 now, we keep it fixed, and we don't change it anymore. So now we have J0 and J1. Now we can put 2 atoms of type B in the crystal, as arranged there. So, okay, then we can say, okay, the energy of this thing is basically the energy of the pristine crystal plus 2 times an atom of type B. So this is represented by the J1 interaction. But we know that this is not exactly the energy, because there is an energy contribution due to the fact that these atoms are close together. Therefore, we make an ab initio calculation. We know these parameters, and then we take the difference between this and this part, and we can get another energy contribution that we call J2. As you can imagine, these additional contributions will be smaller and smaller as long as we are increasing the size of these arrangements of substitutions. So now we go to another one. You see this distance is a bit larger than this one. So one can imagine that the interaction associated to putting 2 atoms here is not the same as putting in this direction. Therefore, we now estimate the energy by the pristine energy plus twice having an atom B plus another interaction that we call now another 2-point interaction that we call C2 prime. Therefore, again, making the difference, we can get this parameter. Then you can put it there, and we get another parameter in the same way. And then you can put 3 of them. Then you have the pristine, 3 times J1, 1 times J2, 1 times J2 prime, and then another parameter that we call J3. That is an interaction associated to having 3 atoms together in this arrangement. Therefore, once we have all those parameters, we make an arbitrary configuration, and then we can estimate the energy with this parameter that we obtained before. So it doesn't matter which configuration you put, whenever you count precisely how many of those interactions you have in your system, then you are done. For instance, for C2 prime, we have 4. This is 1, 2, 3, and 4 of them. Okay, so this brings us to certain concepts, because, okay, this is done by hand, but we want to do it with a certain with a certain code and do it in a more systematic way. Therefore, we define some concepts. One concept is the concept of clusters. So clusters are basically set of symmetrically distinct crystal sites. For instance, this is a cluster. This represents a cluster, and there are many that are symmetrically the same. This one is the same, this one is the same, this one is the same. And then you can define several of them. All this we used in the calculation before. So basically, we call it alpha, and this is a set of sites 1, 2, or whatever. For instance, we can indicate this cluster if we enumerate the crystal size like 1, 2, 3, 4, 5, 6, 7, and so on. So this cluster would be just a set 1 and 2. And then we have another quantity that is the multiplicity of the cluster. The multiplicity of the cluster is how many symmetrically equivalent repetitions of this pattern you can find in the structure. In this case, there are 16. You can count them 1, 2, 3, 4. These 4 times is you have 16 times this cluster. So then we have defined what is a cluster. We now have what is the multiplicity of the cluster. And then another important element in the theory is the configuration vector, something very simple. We basically enumerate again the crystal size, 1, 2, 3, 4, and so on. And then if atom of type A is sitting there, then we put the number 0. And if we have atom of type B, we put just the number 1. Therefore, for this configuration, we will have 0, 1, 0, 0, 0, 1, 1, 0, and so on, like this here. Okay. Another concept that is important to build the method are the cluster correlations. The cluster correlations basically counts how many times a given pattern alpha is found in a certain arrangement or structure that we call S. In this case, for instance, the frequency that this pattern is found in this structure is 1 over all possible patterns that you could find there, that is 16. So basically, or you could say this is the probability of finding this pattern in that structure. If all were red here, this could be just 1. If there is nothing like this here, then you have 0. So a way to write it this in a more self-contained way is like this formula here. So you have 1 over the multiplicity of the cluster. So this is basically the correlation between the cluster alpha and structure S. So you have 1 over the multiplicity, and then a sum over all distinct repetitions, symmetrical distinct repetitions of this cluster, and then the product of the configuration vector. For instance, here you will have, this is 0 times 0 is 0, 1 times 1 is 1, 0 times 1 is 0, 0. So you have all 0 contributions except this one. So you will get this number. This product, the sum of all those products will give you just 1. And you have the multiplicity that is 16, then you have this number. So when we have all those elements well defined, we can basically write this expansion in terms of clusters, where you have basically a sum over all symmetrically distinct clusters, the multiplicity of each cluster, the cluster correlations for this structure, and these shades that are the interaction coefficients that we found before. So basically, this is essentially the same as an expression like this one. It's a sum over the different clusters, and these are the multiplicities times the correlations. So, but we usually don't do the way of putting first 1 atom, then 2 atoms, then 3 atoms, and so on. What one usually does, one has different structures, and then you will try to get these parameters from structures that are not so well ordered. Therefore, you have what we call a training set. Suppose you have this structure, you calculate the ab initio energy, you call it E0. Then you have a different structure with a different concentration and different arrangements, you call E1 and E2 and so on. Then with this set of energies, you build a vector, the energy of structure 1, structure 2, and the number of structures. Yes, this is the size of the training set. Then you build a pool of clusters that can be as large as you like. So you have basically the pristine structure, and you find different patterns. Then you build a matrix, that is a matrix of the multiplicity times the correlations. Here, every column of the matrix represents a different cluster, and every row represents a different structure. Then, once you find the coefficients, that I will say in a moment how you find them, you can basically write the energy as we did before, and you can represent in a matrix form in this way. So, the question is how to find the interaction coefficients. To do this, we basically want those interaction coefficients that will minimize the difference between the calculated energy with a cluster expansion and the ab initio energies. So, and a good measure of the error is the mean square error. So you simply calculate the sum over all possible structures. This is the ab initio energy of a structure S. This is the predicted energy with this formula. Also for a structure S, you put it to the power of 2, and then you basically minimize it with respect to the interaction coefficient. So you basically calculate the gradient of this function. You know that this depends on the chase, and you equate it to 0. And then you find the analytical solution, that is basically this formula here, where this X is the matrix, the X matrix. So if you have X transpose times X to the -1, X transpose, you multiply by the ab initio energies, and you get the interaction coefficients. So this is a systematic way to perform the cluster expansion. However, this usual procedure has some troubles. It is highly sensitive to noise. So what it means, suppose your K-grid is not high enough, or you have certain noise in the data, then basically those parameters, find in this simple way, will be prone to feed noise. So then whenever you want to predict for a new structure, the predictions will not be so good. Also, in this simple way, you cannot invert this matrix if the number of clusters is larger than the training set. So you are limited in the number of parameters that you can use in your model. In order to overcome those drawbacks, you add a regularization term to the optimization procedure. So we have the mean square error, and you could add, for instance, this term here, that is basically weights the interactions to the power of 2. So this would basically favor that would penalize large interactions. So this is has an effect of shrinking of the interactions, but it is also nice because now the problem is regularized, and you can put more model parameters than structures in your system. So you can test over very much larger sets of parameters in your model. So we call this objective function. So now it's the mean square error plus this term. And now for this simple L2 norm, maybe you may have heard already in the previous talks what is the L1 norm or the L2 norm. So this is an L2 norm. You find this solution that now what you invert is not the matrix X times X, but this matrix plus some term here that makes it invertible for a larger number of parameters. However, so we have been here more concentrated on finding the best fit, but this does not guarantee that your model will be good for predictions of new materials. So in order to improve the model construction and make it better for predictions, you could build a validation set. So you add a few more structures that we call E validation 0, E validation 1. Then what you do is you propose a set of clusters, you optimize this objective function, and then you calculate what is the prediction error just for these two structures. Then you change the set of clusters, you optimize the objective function, and you calculate again this thing. And then you basically select those clusters that minimize the predictions on new structures. So this is called the cross-validation method, and then there is a number basically that represents this quantity. Is a cross-validation score. So you can use, for instance, the leave one out cross-validation. Okay, there is another problem here. Usually you don't have so many computation time, so you cannot make a separate set and leave it out from the model forever. So what you do, instead of having this, you will not have this. So what you do is just you remove one structure from here, you build the model with the remaining structures, and then you calculate the prediction error on the structure that you removed. So you do this for every one of those structures. So this is the property, the ab initio property. This is the ab initio property built with a model where you extracted that structure. And this is the cross-validation score. So you will basically select the set of clusters or model parameters that would minimize this quantity. So, but there is a problem here because usually the number of clusters is very large, and testing every possible set of different clusters is what is called an NP-hard problem that cannot be solved in a polynomial time. Also, then, as this is basically impossible to solve for the absolutely all possible set of clusters, then you need some physical intuition to say, okay, maybe smaller interactions are larger than, interactions for small clusters are larger than interactions for larger clusters. Then you would try to form a set of clusters composed of small clusters, but this is not always the best model. So what you can do to avoid this problem is to use the technique of compressed sensing. So instead of using an L2 norm as a penalization term, you may use the L1 norm. The L1 norm, instead of having here the interaction coefficients to the power of 2, you just take the module of those. This norm is also called Manhattan norm. This is in reference, the Euclidean distance would be the shortest distance between 2 points in Manhattan, but the Manhattan norm is what you would do if you go walking from one star to the other. This problem can be also represented mathematically in a different way as the minimization of the mean square error constraint to this this condition that the sum of all norms is equal to some number. You can do the same also constraint expression for the L2 norm. When you use the L2 norm, for instance, these ISO values represent the ISO values of the mean square error, and this ISO value represents basically the ISO value of the J squares, not this one, of the L2 norm. So you basically want to find the minimum of the mean square error constraint in this circle, and you will find some dot. And you see that this dot has interactions for J1 and J2 that are different from 0. But if instead of the Euclidean norm you use the Manhattan norm, that basically the ISO value of this expression is a square here, then the minimum will automatically give you the value for the interaction J2 exactly equal to 0 and some finite value for J1. So this technique does two things at the same time. It gives you the optimal coefficients and also what are the most relevant coefficients in your model, because it creates what is called sparsity in the model. So you have a large bunch of clusters, and then you minimize this objective function, and then you will come out with many interaction coefficients that are exactly equal to 0. Therefore, you have a model that is sparse, and you always will favor sparsity. So this is the one-shot solution. This is what I just said. This is also is very good for what is called noise filtering. Has a drawback as respect to the L2 norm that you have to solve it numerically, but there are very efficient methods for this, like lasso. So this is, I wanted to mention here two developers of our code here. One is Maria Troppen, she works on the lasso implementation in the code that I will talk in a moment, and Christopher Sutton is with a Sprigbergman iteration method. Okay, then how all this is done in practice? You basically start with, you need an initial cluster expansion, so you need some initial data and some initial set of clusters, whatever you choose. And then what you have a crystal, a supercell, and usually what the available codes do is a full structural enumeration. So you basically, suppose you have this crystal, and then you want to know all possible configurations with 4 atoms or with 4 lattice sites. So first you have to consider all symmetrically in equivalent supercells of 4 sites. These are represented here. This is one, this is another one, this is another one, and so on. And then for every one of them, you should consider all possible decorations of this cell with atoms A and B. These are represented here in a binary form. So this is basically what comes here in the full structure enumeration. Then what you do, you have to make a structure selection. So of all a huge number of structures, you have to say for which of them you will perform ab initio calculations. So one possibility is, okay, so I just pick randomly some structures. Another one is you have some initial cluster expansion, so maybe you can calculate the predicted energy for all of them and calculate the ones that are smaller in energy if you are interested in ground states. Also, you can add those structures that would minimize the variance of the predictions, or you can also make an analysis of the correlation in correlation space of every structure. You know how to calculate the correlation vector, and you would like that a set of structures that are randomly distributed in this correlation space. So these are usual techniques that are used to select which structures to perform calculations on, but those requires a full structure enumeration. Then you have to select the clusters. This I already talked about that a bit. So the first option is physically funded. You would say, okay, I will try to take those clusters that are the smallest possible in size, what we call radius. The radius could be the maximum distance between two sites in the cluster, and the smallest number of points. So you would favor in your set clusters of 2 points against cluster of 5 points, because you know cluster of 5 points may represent the smaller interactions. Another way to select cluster is through genetic algorithms. This has been done already. And another way, I would say this is the one of the most efficient and a nice ways to do it is by using compressed sensing. But there is a drawback on this approach, that this very first step that usually the codes do is that they pose an unsurmountable problem for systems with large parent cells. So what I am talking here, so for instance, I will give some examples for, this is a system, what I mean with a large parent cell. Large parent cell means that if you take the smallest possible cell of the crystal structure, it contains many atoms. With many, we are talking about around 30. If it contains more than 30 atoms, we call it big or large. So this is a clathrate material. As you can see, this is, for instance, this is the case for a silicon clathrate. So every blue, green, and red side here, you would put a silicon atom, and then it has some cavities that you can put different elements. And then those atoms in the lattice you can replace by different species to optimize certain properties. So the number of sites in this, without counting the guest atoms, is 46. And the number of symmetries of this crystal is 48. So here you can estimate how many symmetrically distinct configurations you will have in the crystal for a given number of substituent atoms in the crystal. So this is plotted here. In the x-axis, you have the number of substituted sites in the crystal, and in the y-axis, you have the number of possible structures in this full enumeration. So the numbers, as you can see, are huge and are much bigger than for usual simple alloys. If you, for instance, estimate with a normal computer, let's say, how much it takes to perform to calculate the predicted energy for all those structures, it could take around 2 months for 10 substitutions, or 30 years for x equals 16. So this usual approach is obviously not an option for this kind of materials. So, for instance, we have tried this system with the code ATAT. This is an automatic toolkit for building cluster expansion models. And if you put already 3 aluminum atoms, the counting of structures already gets stuck in more than 1 day. Also, what is big for Uncle? Uncle is another cluster expansion code. There is this reference here for a crystal of 32 sides, 17 substitutions, with this number of symmetries that is much larger than for this system, for instance, and it takes around 8 hours already for this size. So for 46 sides, we are lost. So then the question comes, are those full enumerations essential for the method or not? So maybe they are essential if you want, with 100% certainty, to find the ground state structure, or the most stable one. But you know always that you have you always use a truncated cluster expansion, so the model is never absolutely precise. Also, you have numerical errors in the ab initio calculations due to k-grid conversions, due to different simulation parameters. And in alloy physics, we need a reasonable description of low-lying states in a small energy range. So you, in principle, do not need the absolute ground state to get a good description of an alloy system. So we propose a change of strategy for large parent lattices. This is the limits around 30 atoms. Is to that consists on a partial sampling of the physically relevant energy region for an alloy. And this implies an astronomical reduction of computational costs when, with astronomical, I mean numbers like this one. So here is okay, I showed this already. Okay, these are target systems are, for instance, this clathrate alloy, or these other alloys that are used for thermoelectric applications. Here you can see the unit cell of this object is huge. There are many sites that you can substitute. So now I will explain a bit how is the workflow of this different approach. So basically you start with an initial set of random structures, then you perform ab initio calculations for those, and then you make an initial cluster expansion. Then once you have this first cluster expansion, you make a metropolis sampling to go to low-lying structures, if you are interested in the ground state. Then from this sampling, you get some what we call lowest non-degenerated structures. And if you first find some low-lying structures, then you will find some that are low, but a bit above those. So basically, you find the lowest energy structure that is non-degenerate to one low energy configuration that you have already found. Then you perform ab initio calculations for those LND structures. You make a new cluster expansion. You check the cross-validation score. If it is too large to make predictions, then you come back and make another sampling, and then you iterate here. Whenever you are satisfied with this cross-validation, this has to do with which precision you need in your predictions to have a good description of your system. Then you can make predictions of different properties. So this in any of the steps, you do not do any full enumeration in any of those steps. So I will show here how it works in practice. This is taken from a master thesis from Martin Kuban here in HAU. This is for the ternary clathrate. Basically, you have as I showed before, you have the guest atoms. These are kept fixed. These are called spectator atoms because they do not take part of the cluster expansion. But what takes part in the cluster expansion are these three elements: nickel, germanium, and vacancies. That vacancy is also considered as a species in the metal. So you start with some, so here you have the nickel content in the clathrate. This is, I think, an example for, okay, I don't remember exactly how many vacancies there is in this plot, but this plot is for a specific number of vacancies. And then here you have the energy of mixing. Okay, then you have some random structures, and you perform the ab initio calculations, and you make a cluster expansion. Then you go and perform a sampling, a metropolis sampling. And then you search for low-lying structures, as here. Then you basically identify those structures that are marked here with these green squares. And then you perform ab initio calculations for them. You see, in some cases, the predictions are good. In some cases, they are not so good. then as you are not, this means a large cross-validation. So you are not satisfied with it, then you come back and you perform a new metropolis sampling with a new cluster expansion, and then you will identify those lowest non-degenerate structures. Sorry, and you do this several times, and at the end what you get is something like this. This is for 0 vacancies, for 1 vacancy, for 2 vacancies. So all black dots here represent the ab initio calculations. The green squares represent all the predictions with the cluster expansion. The red dots represent the ab initio data for the last iteration of the algorithm. As you see, they are not the lowest one because they are the lowest non-degenerate. So you first found this one, then you found this one, and then you end up with something above. And then here, what are indicated are the ground state structures that were predicted with the method, with these crosses. Okay, so then there is a question here. We are not making full enumerations. Also, the way we are selecting structures is a bit biased because you are basically sampling more structures of low energy. So the question is this good enough? What we found here is this for a binary cluster, aluminum silicon. It's different from the other was ternary. So here is again the application of the method, and we found the ground states. And here indicated are the cross validations for this region here and this region here. What you can see, the cross validation in the full set is, for instance, in this case, I will concentrate on this case, is 1.43. But then if you go and select the region that is low lying energy, you find out that the cross validations are smaller. So basically, in fact, by basically training the model with low lying structure, we are basically increasing the predictability power on this region, on this region. But if you are interested in that, then this is good. So there is nothing bad on avoiding full enumerations and going to partial samplings. Okay, so once you have a model that allows you to calculate any structure for any possible configurations, then you can access the thermodynamics. Basically, you want to study the thermodynamical stability as a function of composition and temperature. So this is covered by the Gibbs free energy. That is basically the sum of the free energy plus pressure and times volume. So usually the free energy can be calculated as an integral between some certain temperature and the temperature that you are interested in. And where here, this is the internal energy of your crystal. This is what you calculate with the cluster expansion. The drawback of this way of doing the calculation is that to obtain the internal energy at every possible temperature in this interval, you have to perform a Monte Carlo simulation at every different temperature. So this can be avoided by another method that is also implemented in our code that is called the one-Landau method. In the one-Landau method, you find the configurational density of states that is represented by this quantity and does not depend on temperature. So it requires only to make a single sampling or a simple, instead of making several Monte Carlo simulations at different temperatures, you have to do a single simulation to find this quantity, and then you can find the free energy at arbitrary temperatures. Also, the question arises, okay, here we are only accounted for configurational entropy. So then what if you want to add the electronic entropy or the vibrational entropy? For that, you use a coarse graining procedure. Sorry, I think this is repeated. Yes, coarse. Okay, so this is basically what I said before, sorry. You use a coarse graining procedure that basically takes into account the fact that the electronic degrees of freedom are much faster than the ionic degrees of freedom. So these are the vibrations of the crystal, and these are also much faster than the configurational ones. So means electrons move much faster than the ions, and the configurational changes in the system of swapping species inside the crystal, this is much, much slower than all of this. So what you can do, this would be the exact partition function of a system where you have to sum over all possible configurations, or possible ion positions, or possible electron positions, instead of calculating this object, what you calculate is the sum over different configurations, and here, instead of putting the energy or the internal energy for the configuration, you put the free energy that contains the electronic and vibrational free energies in the expression. So you basically make a cluster expansion on the free energy, and this will give you, in the thermodynamic analysis, the correct full entropy. So here I will give some brief examples on the application of the thermodynamic analysis for some of the systems that we have studied using cell. This is an example for this class rate for the certain compositions x equals 15. What we found is that for the ground state structure, this system has an electronic band gap. This is the energy, and this is the electronic density of states. You see, this is the ground state structure that has a band gap. But then at the same configuration, at the same composition, configurations that are higher in energy have a lower band gap or are just metallic. So we basically studied this problem, and we found out that this is everything done with a cluster expansion, that the structure presents what is called an order-disorder transition. Here, these lines here represent how many aluminum atoms there are in every side of the crystal. So at low, this is axis is the temperature. So at low temperatures, the crystal is ordered, and at high temperatures, it gets disordered. So the occupations or the fractional occupations in the crystals on the different crystals are exactly the same. This is basically a signature of disorder. So in this order-disorder transition, you can calculate the finite temperature band gap with the one-Landau method, where the band gap is predicted with the cluster expansion. As you know, with the cluster expansion, you can train it to calculate energies, but also you can train it to calculate band gaps, for instance. So if your input data is band gaps instead of energies, you can also calculate that. This is, for instance, the specific heat for this system that has a peak at the transition temperature. So here is another example for a surface system. This is hydrogen on zinc oxide. Also was studied using the one-Landau method with cell. Okay, I will not go too much into detail, but I wanted only to say that you can perform also all this analysis for a surface system instead of bulk systems. So here is an example of the result for this system. This is, you can get the hydrogen coverage at different temperatures in the surface and this sort of things. So cell basically consists of several, it's a Python package and also a command line utility. So you basically can write by writing commands, as Christopher will explain in some moment for the tutorial. Or you can also import it as a Python package in some script, and you can perform a tailored cluster expansion to your needs. So have several models for different purposes, and some packages for compressed sensing, for the one-Landau, nested sampling, split Bregman, etc. It uses a couple of utilities from ATAT to generate the clusters and to generate the correlation matrix. Also, Cell has been, there is now a web interface for the code cell in the Nomad Analytics Toolkit. You can look at it here. So basically, there is a tutorial on, for an example, of a silicon germanium binary alloy. So you can set your parameters, what is the maximum numbers of points in your cluster, what is the maximum radius, how many samplings you want, sampling steps you want to perform, the temperature of your sampling, and so on. So here it shows the optimization of the cluster set. For instance, this is the number of clusters. This indicates basically the cross-validation score, the mean square error. So it selects automatically the cluster set that is best for your model. Also, you can make predictions of the convex hull of alloys. Okay, so I go to the acknowledgements. The code cell has been developed in the group of Claudia Draxel. The developers, current developers of the code are Maria Troppens from Humboldt University, Martin Kuban from Humboldt University, Christopher Sutton from Fritz Haber Institute, and Axel Hübner also from Humboldt University. Thanks.